Implementing secure cryptographic algorithms is hard. The code must not only be functionally correct, memory safe, and efficient, it must also avoid revealing secrets indirectly through side channels like control flow, memory access patterns, and execution time. Programs that have these properties are said to be constant time. Lots of recent work has focused on helping programmers write constant time code through type system, program transformations, and automate the verification of constant time implementations. Unfortunately, these efforts are crippled by speculative execution. Even if programs control secrets closely through bounds checks, the processor can simply ignore them when executing speculatively. An attacker can exploit this behavior by leaking secrets to the cache, where they can be recovered through cache timing measurements. In principle, programmers can insert fences to stop speculation and so avoid speculative leaks. In practice, however, fences pose a big problem. Programmers can restore security by conservatively inserting fences after every load. However, this will cause a huge performance overhead. Alternatively, they can rely on heuristics to insert fences in their code, but give up all guarantees about the absence of side channels. This is because even missing a single fence can expose the whole process memory to the attacker. This risk is so serious that browsers like Chrome and Firefox isolate secrets from untrusted code in a different process just to avoid the risk altogether. In this work, we propose a solution to improve the situation. Blade is a new, fully automatic approach to provably and efficiently eliminate speculative leaks from constant-time cryptographic code. The key inside of Blade is that to prevent speculative leaks, we don't need to stop all speculation like memory fences do. Instead, we only need to stop speculation along specific data paths. In particular, we only need to cut the data flow from source expressions that speculatively read secrets to sync expressions which leak them through the cache. To do that, we propose and formalize the semantics of a new abstract primitive called protect. Unlike regular fences, protect stops speculation only for a given variable. For example, this protect statement ensures that the value of e is assigned to x only after e has assumed its stable, non-speculative value. Although protect should be ideally implemented in hardware, for backwards compatibility, we implement protect in software via speculative load hardening. Blade inserts protect statements to eliminate speculative leaks. First, Blade identifies source and sink expressions in a program. Then, it detects data flows from sources to sinks. And lastly, it inserts protect statements to cut the source-to-sink data flows. The program on the right is now secure because the protect statement prevents any secret introduced by the source from reaching the sink. In order to detect speculative leaks, Blade tracks speculative data flows by means of a static type system. The type system conservatively approximates the dynamic semantics of speculation using two types, transient and stable. Expressions are typed either transient if they can contain transient secrets, or stable if they cannot. The type system performs static taint tracking and treats transient expressions as tainted. The typing judgment for expressions simply propagates the transient taint, and the judgment for comments restricts the use of transient data to avoid leaks. Intuitively, programs that are well typed according to this type system are free of speculative leaks. One of the goals of Blade is to enable source-level reasoning about the absence of speculative leaks. In order to prove our type system sound, we need high-level reasoning principles. However, the effects of speculation manifest only at the very low machine level. Clearly, there is a mismatch between the two. We reconcile this tension by giving the first source-level semantics model of speculation. In this video, we have presented Blade, a new, fully automatic approach to provably and efficiently eliminate speculative leaks in unannotated cryptographic code. Blade statically detects data flows from transient sources to stable sinks and synthesizes a minimal number of fences and masks to eliminate potential leaks. We have implemented Blade in the Cranelift WebAssembly compiler and evaluated our approach by repairing several verified, yet vulnerable, WebAssembly implementation of cryptographic primitives.